This video applies blower door pressure test measurements to the initial setup of air leakage paths in a numerical simulation model. What we want to do is create a virtual blower door test, after which the facade orifices are used to assess infiltration risk. A bit of background. One uncertainty in building performance prediction is air movement resulting from weather patterns, user interventions, the operations of mechanical systems. Some things we can physically measure, but there are often hidden faults within the fabric of the building that are problematic. Simulation tools present us with multiple approaches to describing and assessing airflow. For example, ESPR supports everything from deity-imposed airflow rates to computational fluid dynamics. Each is nominally associated with a stage in the design process, the available information, and the current design question. Yes, there are moments early in the design process where posing a what-if related to an arbitrary flow regime might give us some useful information. After that, if our tools support it, we might be much better off if we allow the simulation tool to do the heavy lifting. The thing is, practitioners often act as lazy deities, and hallucinations can creep into workflows. If we want to go beyond user-imposed flow rates and describe leakage paths for our numerical models to assess, well, it turns out some aspects of the workflow straightforward and others involve hidden faults that are difficult to characterize, and that's where it gets interesting. We might begin the task by setting some defaults for leakage paths. Some things, of course, yes, we can measure, so the depth of undercuts. Those are straightforward things to do. We know the size of doors. The setting of crack widths would take quite a bit of experience and probably some iteration to tune such values. So, here's an example of a straightforward task. Leakage paths associated with doors, openings, and grills. Model surface that acts as a door and marked as an undercut. Well, that could reliably drive the creation of a relevant flow component. Window frames with a trickle vent? Well, those are fairly well supported. Leakage around a crack at the perimeter? That's a judgment call. Yes, if I do a smoke test during a blower door, I get some hints about infiltration risks at a window. But many facade faults are hidden behind wall plugs and service openings. The thing is, they add up. I ran workshops for design teams seeking qualification in Passive House, showing participants the caustic impact of snagging and how to leverage blower door and smoke tests. In this video, we're looking at other ways to leverage blower door testing. And sorry to rain on your parade, but patterns from smoke tests are indicative rather than qualitative measures. It's beyond this video to give you a full experience of the physical test. To be credible, our virtual test needs to follow the same rules, so it's necessary to create, yes, a virtual blower, and we can use a fixed boundary pressure set at 50 pascals for this. But we also need to ensure air can pass between rooms and that windows are closed, among other things. A blower door test does, in the end, give us an aggregate flow for all of the rooms in the tests. Let's see what we can do with that. ESPR and quite a few other simulation tools include an orifice flow component. And although it's always been possible to set attributes to eventually match a given flow at a given pressure, doing so manually is rather painful. Thankfully, a team in Canada implemented an empirical method, and in that is some code that helps size an orifice based on blower door inputs. I decided to leverage this to automate the process. First step, after putting in the code, was to simply provide a report about the relevant attributes of the orifice, which I could then test out. The second phase of the work was to leverage recent work on an icon-based network creation tool to augment facilities that already could populate a grid with room nodes and wind pressure boundary nodes. I added in sized orifices for each of the rooms. Users could then use the net utility facilities to reposition the icons and connect the nodes and components. The beauty of this approach for some is that the thermal model is untouched. You could set up a virtual blower door what if. If it didn't work out, well, you could simply remove a couple of files and carry on. All we need is a short duration assessment with the blower door in place to confirm that predicted airflows are a reasonable fit to the actual blower door measurements. And it is a trivial exercise to remove the blower and allow subsequent assessments of infiltration to be evaluated by way of the remaining facade orifices. Would such calibrated orifice make a better starting point than opposing flows or guessing what can be measured? Well, let's find out by following a work session in the context of a 4-room test model that you might have seen in recent videos. The front right room entry door, that's where we'll put the blower door. However, before we go into prescribed fluid flow, let's review the contents of the rooms. Some of the surfaces have been partly attributed with their uses. I normally do this kind of thing for clarity, so we know which surfaces are doors and frames and windows. For the room where the blower door will be placed, we'll place the infiltration orifice on another surface to avoid confusion. Now let's go into the overall menu that allows us to choose how we want to approach airflow. Yeah, we've got lots of choices. In this case, we're going to choose blower door test to minimum flow net. We're asking the same questions about the blower door as were involved in the run-up to invoking the net facility. Again, we're asked, where to place the blower door, what's the air change rate in the physical or imagined blower door test, and we're also asked to select a surface in each of the rooms for the calibrated orifice to be placed. One of the rooms doesn't have any windows or frames, so in that one I selected one of the facades. And the ceiling void, well, it might not be occupied, but is more than likely to host faults, probably more than any of the other rooms, simply because staff on site tend to think nobody will actually notice the quality of that part of the build. If you're skeptical of this kind of claim, you haven't poked your head around enough ceiling voids. Trust me, document what and why while that it's fresh in your mind. In a few weeks, such information will come in quite handy. And now we're presented by the initial nodes, components, and connections. You can see the blower door on the right, and each of the rooms does have a connection to the outside. What's missing is a critical part of the physical test. We need openings between the rooms. How we add these openings? Well, we've got choices. Let's try one way where we just continue to use the facilities within the flow network interface. Let's start with a door between the front left and right room. We go into the Components submenu and ask to add a flow component. We give it a name. We then select the available component types. What we're looking for is a type 130, which is called a specific airflow door. Actually, what it is a method to allow bidirectional flow depending on the evolving temperatures and pressures in the adjacent spaces. And we're confronted by the need to dimension the opening and set flow attributes. It's kind of a bit frustrating if we don't have the information to hand. And then we're asked to locate the component, and so we have to select a room and a surface. And now we need to connect this component to the network by identifying the nodes on each side. So we go into the Connections menu, where we go through the process of selecting the two nodes and the component. Now, if I had to do this a dozen times, it would become seriously unpleasant. Is there an alternative to all of these keystrokes and all of this remembering of trivial details? Well, yes, there is. Let's rewind, go back to, and do a bit of preparatory work before we enter the blower door facility. And for this, we'll use the facilities within the thermal zone surface attribution. Noise is off. I made a pass-through and completed the attribution of many of the doors and openings needed for the virtual blower door test. So let's make a traverse of the rooms so we can see these changes. Now, we've arrived at the back right room and find one of the doors is not completely attributed, so let's correct that so you can see what that process is like. When we return to the main flow menu, we can see that 6 doors have been defined. We can now step through the process for filling in the blower door measurements. Been here before, identify where the blower door will be mounted. Specify the air change rate at 50 pascals. The value 1.2 is well beyond what would be expected in a passive house project, but it's not bad for conventional construction. And for each of the rooms, we nominate the location for the orifice. Need I say that careful bit of documentation is well worth the effort. And here in the wireframe, we can see the resulting nodes, components, and connections. Looking at the nodes menu, we see there's wind-related boundary nodes have been added. Looking in the components, we have a number to add, but we're in a better place to fill in the remaining flow paths needed for the test. Again, we use the wireframe view to quickly remind ourselves of the gaps we need to fill in. Let's save the current network and then exit and shift focus to the zone geometry facilities. I choose the surface attributes option and go into the first room. If we select the door between the rooms, a bit of background logic figures out that, we have a fully defined flow attributed surface, but there's no similar definition in the flow network, and it asks us what we want to do. Of the choices of selecting a component from the network, creating a component to match this surface, or ignore it, we take the middle option. And guess what? The position of the door and its current dimensions and some of the default attributions like the discharge coefficient are passed into the flow data structures. Because the door surface knows what's on each side, the logic in the background can find the relative flow nodes and creates the necessary linkage. Much less hassle. Save the zone information, move on to the next room. Here we need to add in the opening to the back right room, following the usual process. Again, we save and move on to the next room, which is on the back left. Here, there are two connections that we need to make. The first is the opening to the back right room. And remembering that there's a grill in the ceiling void, we need to associate that into the network, given that there will be faults in the ceiling void. So we want that flow opening to be the full area of the grill. And then we shift focus to the back right room. Those two openings have already been defined when we were passing through the other room, so there's nothing to be done there. Did this work? Let's return to the main flow menu and have a look at the network details. Looking into the list of components, we see that we have openings and the grill defined. Looking into the list of connections, we see that internal linkages between the rooms, yes, they're in place. Just to be paranoid, let's re-step through the internal nodes and check that they're still correctly linked to the thermal zones. Now, to actually test that the virtual blower door has been set up correctly, we only need a few days of simulation. For the flow rate at 1.2 air changes per hour, we should be looking at roughly 130 meters cubed per hour. And that's indeed what we find is going into the space. The flows at the three rooms are roughly the same as expected, and the flow to the ceiling void is less, also as expected. Now it only remains to do a quick tidy to remove the connection to the blower door. We now have a model with facade orifices which have been correctly sized for the 50 Pascal case and can now be subjected to the normal weather patterns of wind speed and direction to explore the impact of infiltration over time. Let's run that and see what happens. Hey, this is a small building. Flow networks solve with very little computational overheads. So we're going to do an annual assessment. We're going to monitor the assessment as it progresses by tracking the temperature in each of the rooms. Again, I'm adding some documentation so that in a few days I can still remember what in the world this run was about. And in a dozen seconds on a small form factor Dell computer that's quite old, the assessment's done. And we can see that the temperatures vary across each day simply because the rooms are conditioned only during office hours. Let's take a quick look at the predictions. Choose resultant temperatures in each of the rooms. Yeah, it's a similar sort of spread over the year. Let's clear that and look at the heating needed in each room to reach 20 degrees during office hours. At first glance, seems kind of reasonable. Needs a further look to learn more about it. And then we'll move on to cooling demand. Again, at first glance, I'm not surprised. Now, the magnitude is relatively small because the facade, after all, is very high specification and there's not a whole lot of south-facing glazing. If we turn our focus to the energy impact of air entering from the outside, in ESPR it calls this infiltration, we see it does vary over time, but the magnitude is again constrained. If we add to this the impact of airflow between rooms, which ESPR calls ventilation, we'll readjust the axis scaling so those bidirectional flow components allow the excess temperatures in some rooms to flow to the adjacent cooler spaces. This is one huge difference in using a flow solver rather than a user-imposed flows. Another performance view is to look at the sensible heating and cooling required in each room over the year. As with many buildings with high-performance facades, the cooling needed to keep the rooms below 24 degrees during office hours is often rather more than what is required for heating. If you look at statistics for the energy impact of air movement, we again see that the heat transported in the air moving between rooms can be greater than that implied by air passing through the facade. And this happens even when the case of each of the occupied spaces have been conditioned with the same thermostat settings. Lastly, we can review the overall energy balance in each of the rooms over the year. The energy impact of air movement within that energy balance could provide a useful guidance for those who know how to read such tables. So, how does this blower door approach compare with, say, imposing fixed airflow rates using something like the divide by 20 blower door rule? Well, that's the subject of the next video.